You know, we've all dreamt about it, right? Teleportation, beaming from one place to another in the blink of an eye. Well, what used to be pure science fiction is, believe it or not, starting to become a mind-bending reality. So let's dive into how scientists are now teleporting information using the truly weird and wonderful rules of quantum physics.
All right, let's get right to it. Is teleportation real? And the answer is yes. But, and this is a big but, it's probably not what you're picturing. We're not talking about beaming people across the galaxy Star Trek style. When scientists talk about teleportation, they mean something way more fundamental and honestly, maybe even a little stranger.
Okay, so here's the fundamental difference. Think about our entire global communication system, your phone, the internet, all of it. It works by physically sending stuff, like electrons down a wire or photons through a fiber optic cable. Quantum teleportation just breaks that rule completely. The actual particle carrying the information never makes the journey. The information itself, it just appears at the destination.
Now, to really wrap our heads around this, let's use a simple analogy. Imagine you're sending the blueprints for a building, not the actual building itself. So this information that's getting teleported is what physicists call a quantum state. The easiest way to think of it is as the complete set of instructions for a particle. It's everything that makes that particle what it is. Its spin, its polarization, you name it. It's kind of like the particle's unique digital fingerprint. So back to our analogy. Let's say you have this incredibly unique, complex Lego model. Now, instead of taking it all apart, shipping the thousands of little bricks, and hoping someone on the other end can rebuild it perfectly, what if you could just instantly transfer the master building instructions? The original Lego model stays right where it is, but an absolutely identical copy appears somewhere else. That's pretty much what happened here, but with a single particle of light.
So this all sounds great in theory, but how did they actually pull it off? Let's take a look at the real-world experiment that made this amazing concept a reality.
And you know, this didn't happen in some perfectly isolated, sterile lab. This was a collaboration between Paderborn University and Sapienza University of Rome, and it took place right across a real college campus. They literally put their equipment in two different buildings and shot a laser through 270 meters of open air to connect them. Now, at the very heart of this experiment is a tiny piece of tech called a quantum dot, and these things are just incredible. They're basically microscopic crystals that act like tiny artificial atoms, but their real superpower, they're like little factories that can produce a single perfect particle of light, a photon, whenever you tell them to, on demand. Okay, this is where it gets really, really cool. The whole experiment rested on solving three massive technical challenges, three pillars that the team had to get just right. Let's break them down. First up, what they call the matching problem. See, in the real world, no two quantum dots are ever perfectly identical. It's like having two guitars that are just slightly out of tune with each other. For this quantum magic to work, the photons they spit out have to be absolutely indistinguishable. So, using these tiny devices and magnetic fields, they literally squeezed and tweaked the quantum dots until they were perfectly in tune, singing the exact same note every single time. Pillar number 2 was all about creating that spooky, invisible connection. And this is where quantum entanglement comes into play. The quantum dot in building B creates a pair of entangled photons. You can think of them as quantum twins. Whatever you do to one instantly affects the other, no matter how far apart they are. So one photon stays behind in building B, while its twin gets sent across that laser link to building A. The quantum bridge is now built. And now for the magic trick itself. It's a process called a Bell's state measurement, and it really just breaks down into 3 simple steps: the meeting, the zap, and the overwrite. So over in building A, the photon that made the trip, P2, meets the message photon. That's the one carrying the information we actually want to send. That's step 1, the meeting. Then in step 2, a special measurement essentially zaps both of them, destroying them in the process. But here's the trick. At that exact instant, because of entanglement, the information, the quantum state from that message photon instantly overwrites the photon waiting all the way back in building B. And that's step 3, the overwrite. The information has jumped. The teleportation is complete. But hang on. How did they know it really worked? That was pillar 3, the proof. In the quantum world, accuracy is measured by something called fidelity. Now, here's the thing. If you were just guessing or using normal classical physics, the absolute best you could ever hope to do is get it right 66.7% of the time. So to prove this was a true quantum effect, they had to beat that number. That was the line in the sand. And they didn't just beat it.
They smashed it. They achieved a fidelity of 82%. That number is the smoking gun. It proves, without a shadow of a doubt, that this information transfer was happening purely because of the laws of quantum mechanics. But, there's another reason this experiment is such a huge milestone, and it all comes down to reliability. It's about being able to print these photons whenever you want. You see, most experiments like this in the past used sources that were totally random. It was like rolling dice. You'd fire up the machine and just cross your fingers, hoping you got the particles you needed. But these quantum dots are what's called deterministic. They're like a printer. When you hit Control P, you know you're getting a page. When these scientists trigger a quantum dot, they know they're getting a photon. That reliability, well, that's a total game changer. Okay, so we've got reliable, on-demand quantum teleportation happening between two buildings. So what? Why is that so incredibly exciting? Because what they've built here is the fundamental blueprint for something much, much bigger. The big problem with quantum signals is that they fade out really fast over long distances. So to build a global quantum network, we're going to need devices called quantum repeaters, little stations that can catch a fading signal, copy its information, and then beam a fresh copy to the next node. And this building-to-building teleportation setup they just demonstrated, it's the exact architecture you need to build one. And that right there is the end goal. A whole network of these repeaters could one day form a global quantum internet. An internet that would allow for ultra-secure communication that is physically impossible to hack. It could even link up quantum supercomputers all across the globe, basically letting them work together as a single planetary brain. So yeah, let's just let that sink in for a second. Scientists successfully teleported the physical instructions of a light particle between buildings. That's not a movie tagline. That is what actually happened. Science fiction meet science fact. So, the key things to remember here are simple, but they're incredibly powerful. This was done with real devices, these quantum dots. It was done in the real world, across a physical gap. And it was powered by reliable, on-demand sources. This wasn't just a win for theory, it was a huge engineering triumph. And that really leaves us with a fascinating final thought. We are now officially at a point where instantly moving information isn't a what if anymore. It's a proven reality. So the question is no longer if we can do it, but what are we, as inventors, as dreamers, as builders, gonna create with this incredible new power? This whole breakdown was based on the landmark research from the brilliant teams at Paderborn University and Sapienza University of Rome. Thanks for tuning in.